Hi everyone, myself Dr. Kumala, working as Associate Professor in the Department of VCE at SJBIT, would like to share this video on basic electronics. The contents what we'll be learning in this video covered in this video is introduction to the materials, the type of materials, the semiconductor materials, the doping, the PN junction diode and the biasing of PN diode. So first of all, before knowing or gaining the knowledge about or learning about p-n junction diode, we need to know what are the different types of materials that can be used or else that is available to frame a p-n junction diode. In the earlier days, you learned about the semiconductor physics in your PUC level, where we came to know that the basic materials which is available or else which can is classified depending upon the conduction of electricity. The types of materials are classified into three. The first one is the conductor, the second is the semiconductor, and the third one is categorized as insulator. Basically, all the types of materials are classified depending upon the conductivity of the material or the conduction of electrons in the material or through it. So now let's understand briefly about the three types of material. The first one is conductor. So what is a conductor? As the name suggests, it is a material which allows or is which can conduct electrons through it. So in simple way, we can define that a conductor is a material which allows the flow of electrons or the charge easily across it whenever an applied is voltage in the device. Always the conductivity of an electron is 10 raised to the power 7 Siemens per minute per meter. So here we have the material which is a conducting material. The voltage is applied. Whenever the voltage is applied, the electrons flow in maximum or as maximum number of electrons flow through the conductor. The best examples of the conductors are silicon, copper, gold and aluminum. Coming for the second type of material, which is the insulator. The insulator is a type of material which will not allow the flow of current through it, or else in the other way we can tell that it avoids the flow of electrons in the material. So the type of materials which will not allow the flow of current through it are defined as insulators. Though there may be maximum voltage what we apply across the insulator terminals, there is no flow of the current in the insulator. And the best examples of insulators are wood, glass and Teflon because they will not allow the conduction of current through it. Coming for the third type of material, which is semiconductor. A semiconductor is a material which has a conductivity lesser than conductor whereas greater than insulator. So a semiconductor material can be defined as a material which conductivity lies between a conductor and an insulator. So how is that possible that a semiconductor can be manufactured? So the conductivity of the semiconductors can be varied by adding the impurities, which is carried out by the process of doping. So in a semiconductor material, whenever an voltage is applied across the semiconductor material, there are flow of electrons in the material which is either lesser than conductor whereas greater than insulator. So the best semiconductor materials are the N type of semiconductor materials and the P type of semiconductor materials, which we'll be learning in the further content of this video. So which are the materials which can be considered to manufacture semiconductor devices? There are three important materials which can use as semiconductor, that is silicon, germanium and gallium arsenide. These are the three materials which are classified as semiconductors. So let's understand about the silicon atomic structure. A silicon has an atomic number which is 14, and where the silicon atom will consist of 14 protons which reside in the nucleus. It also has 14 electrons which rotates around the nucleus. And the specialty of a semiconductor material is the outermost orbit of the semiconductor will have 4 electrons. So a silicon will have an 4 valence electron which is placed in the outermost orbit. So the yellow shades what you are seeing, these are the 4 valence electrons which is placed in the outermost orbit. So coming for the understanding of silicon material. Here this is the bonding diagram of a semiconductor material which is the silicon. Here we can see that each silicon atom shares 4 electrons with its neighboring atoms. So these are the 4 neighboring electrons which is shared by means of the for the neighboring atoms. So what happens whenever an atom is shared with an electron is shared with the neighboring atoms? Whenever there is a sharing in the silicon atom, it becomes a covalent bond. And we can also see that in a semiconductor materials like silicon, there are free electrons which are formed at room temperature, and this free electron which creates a hole or which creates a vacancy, and those vacancies are called as holes. So in this diagram you can see that whenever an electron is released due to covalent bonding, here a hole is generated. So in a semiconductor materials we have free electrons where the mobility is high, and we also find a hole whenever a electron moves away from the atom. So coming for the behavior of silicon at room temperature. At room temperature is for a silicon material exhibits the following properties. For every generated electron, a hole is generated, and always the holes move from one place to another. They are free enough, and also equally the electrons also can move from one place to another. So due to this reason, due to this property in a semiconductor, always we can tell that the flow of electric current is due to two types of charges. One is the positive holes and the other one is the negative electrons. So understanding about the types of flow in semiconductors, as explained earlier, the two types of flow in semiconductors are due to flow of electrons and due to flow of holes. Next, further coming for the classification of semiconductor materials. The semiconductor materials are further classified into two important types. One is the intrinsic semiconductor and the other one is the extrinsic semiconductor. So what is intrinsic semiconductor? A material in its pure form is called as intrinsic semiconductor, and whenever a doping or as whenever an impurity is added to an intrinsic semiconductor, it becomes an extrinsic semiconductor. So the extrinsic semiconductors are classified into two more types, further classified into two more types, where there are P type of semiconductors and N type of semiconductors. Next, further going on with the conductors. So as I told you, a semiconductor material, whenever it's available in the pure form, it is known as intrinsic semiconductor, and it has the entire chemical purity. They are free from impurities. And in an intrinsic semiconductor material, always the number of free electrons is equal to the number of holes in an intrinsic semiconductor. The best examples of intrinsic semiconductors are once again silicon and germanium. The second type of extrinsic semiconductor. So the pure semiconductor material, whenever we add a small amount of chemical impurity to the purest form of intrinsic semiconductor, then the final resulting semiconductor material is what we call as extrinsic semiconductor. There are two types of extrinsic semiconductors, that is the N type of semiconductor and the P type of semiconductor. Now let us understand how the N type of semiconductors and the P type of semiconductors is obtained. The extrinsic semiconductors are converted into N type and P type of semiconductors by the process known as doping. So, what is doping? The process of adding an impurity to the intrinsic semiconductor is what we call as doping. So, whenever we add a trivalent impurity to the pure semiconductor material, then the obtained semiconductor is what we call as P type of semiconductor. Whereas, whenever we add a pentavalent impurity to an intrinsic semiconductor, then the resulting semiconductor is termed as N type of semiconductor. So coming for the first type of semiconductor, which is the P type of semiconductor, or the extrinsic semiconductor, which is of pure type. So as explained earlier, whenever we add a trivalent atom or as a trivalent impurity for the pure semiconductor, it forms a P type of semiconductor materials or P type extrinsic semiconductor materials. So which are the impurities that we can add? The trivalent impurity atoms which can be added to make a P type of semiconductors are aluminum, boron and gallium. These trivalent atoms have 3 valence electrons. So here we can see that in a P type of material, the impurity atoms used for accepting doping have outer shells containing 3 electrons and 5 holes. So suitable atoms with 3 valence electrons are boron, aluminum and gallium. These atoms form covalent bonds with semiconductor atoms, but the bonds lack 1 electron for a complete outer shell of 8. So this is what has been explained in the diagram, and it is also seen that an acceptor doping exists or else also is introduced into the valence band so that the conduction may vary by the process of hole transfer. Since holes can be said to have positive charge, the acceptor doped semiconductor materials is referred to as P type of semiconductors. Like the P type, the materials remains electrically neutral because the total number of orbital electrons in each impurity atom is equal to the total number of protons in its atomic nucleus. So here the term acceptor doping comes from the fact that the holes can accept free electrons. These holes can accept the free electrons. So whenever we consider an undoped semiconductor at room temperature, there are number of free electrons and holes, which results to electron hole pair combination. Next, coming for extrinsic semiconductor, N type of extrinsic semiconductor. Whenever we add a pentavalent atom like arsenic, antimony, or phosphorus to a pure semiconductor, which is silicon, it results in N type of semiconductor material. So the pentavalent atoms will have 5 atoms in its valence electron orbit. Here, whenever the electron is given out, it as the pentavalent atoms as the fifth electron in the outermost shell, one electron will be free to propagate. So they are called as donor atoms. So in donor doping, that is in N type of material, the impurity atoms will have 5 electrons and 3 holes in their electron shells, and they are added to the undoped material. The impurity atom forms covalent bonds with the silicon or germanium atoms. Because semiconductor atoms have only 4 electrons and 4 holes in the valence shells, there is one extra valence shell electron for each impurity atom added. This additional electron produced in this way enters the conduction band as a free electron. Because the free electron have negative charge, the donor semiconductor is known as N type of semiconductor. So in a N type of semiconductor, the free electrons in the conduction band are easily moved around under the influence of electric field. So the term donor doping comes from the fact that an electron is donated to the conduction band by each impurity atom. Next, coming for the majority and minority charge carriers in N type of semiconductor and the P type of semiconductor. So as shown in the diagram, we can see that in an extrinsic semiconductor, which is a P type, the majority charge carriers are always positive holes and the minority charge carriers are always negative electrons. The electrons are the acceptor ions in a P type of semiconductor. In the N type of semiconductor material, the majority charge carriers are negative electrons, whereas the positive holes are the donor ions and the majority charge carriers are positive holes. So now let's understand what is the result when an voltage is applied across a semiconductor material. So now let us consider a P type of semiconductor material. Whenever an voltage is applied to a P type of semiconductor material, the electrons move across positive terminals and the holes move towards the negative terminal. So this is the diagram where we can see that this is the P type of semiconductor. Here, whenever a voltage is applied, voltage is applied, the electrons will move across the positive terminal and the positive holes will move across the negative terminal. When we consider the N type of semiconductor material, it's the vice versa. So whenever we applied a voltage to the N type of semiconductor, the electrons move across the positive holes and the holes move towards the negative terminal. So next, now we have already learned, we have understood about these basic semiconductor materials that is used in manufacturing of a diode. So now let's understand what is a diode. The diode is a two-terminal component which is made from a single piece of semiconductor material which has a positive P region at one end and a negative N region at the other end, and which has a resistivity value somewhere between that of a conductor and an insulator. So this is how a PN junction diode looks as. So there is a P type of semiconductor material and N type of semiconductor material, where this is the junction which is formed between the P and N type. So a PN junction is formed by doping one side with P type of impurity and the other side with N type of impurity. So impurities at PN diode is, on the P side, the majority charge carriers is O's, which has a trivalent atom, and on the other side, in the N type of region, it is the negative electrons, which are the majority charge carriers, and we are the pentavalent atom. So the three important biasing functions of a PN diode. Always a diode can work under three conditions. One is the unbiased PN junction, where the diode is not biased. The second one is the forward bias condition, and the third one is the reverse bias condition. Now let us understand about the unbiased condition of a PN junction. Whenever a diode, PN junction diode, is not applied with any voltage, we call it to be the condition as unbiased PN junction. So under this condition, always the electrons try to diffuse from N region to the P region. The electrons diffuse from N region to the P region, and due to the movement of the electrons, a depletion region is formed due to the creation of ions between the junction. So as we continue with the unbiased PN junction condition, there is a potential barrier which is created due to the depletion region, due to which the ions cannot move from one region to another. So what is this potential barrier value? If we select a silicon material, then the potential barrier voltage is 0.7 volts. For a germanium, it is 0.3 volts. This potential barrier is crossed, and the forward current conduction will take place only after crossing this potential barrier, which is minimum of 0.7 volts for a silicon, whereas 0.3 volts for germanium. So in this diagram, we can understand that whenever a PN junction diode is not biased, then here the flow of majority charge carriers and minority charge carriers across the junction will cancel each other. So the overall current is zero under unbiased condition of a diode. Coming for the second condition, that is the forward bias of a PN junction diode. When do we call that a diode is forward biased? Whenever we connect the positive terminal of a battery to the P type and negative terminal of the battery to the N side of a diode, the diode is said to be under forward bias condition. What will happen when the diode is forward biased? When the PN junction is forward biased, the applied positive potential repels the electrons in the P region, and the applied negative potential repels the electrons in the N region. So the charges move towards the junction. Hence, the potential barrier as well as the width of the depletion region will get reduced whenever the diode is forward biased. Coming for third condition, that is when the diode is reverse biased. When do we call the diode is reverse biased? Whenever we connect the positive terminal of the battery to the N side and negative terminal of the battery to the P side of a PN junction diode, it is said that the diode is connected under reverse bias condition. Whenever the p-n junction is reverse biased, the electrons in the n region and the O's in the p region are attracted away from the junction. So, whenever they are attracted away from the junction, the number of negative ions in the p region and the number of positive ions in the n region increases. Hence, the depletion region becomes wider and the potential barrier is increased. So, since the depletion region does not contain majority charge carriers, the reverse bias junction will have a flow current.